Okay, so good afternoon. This is Sergio Pellegrino. I'm a professor at Galsit, and I will introduce today's speaker, who is Professor Wenbin Yu, a professor at Purdue University. And his academic pedigree, he did his master's work at Tsinghua University, and he was a student with Dewey Hodges at Georgia Tech for his PhD. He is the director of the Composite Design and Manufacturing Hub. And also, he has this very interesting analysis and simulation company that he's involved in called AnalysSwift, for which he is the Chief Technology Officer. He's a remarkably dynamic person. And one thing I like to say about him is that currently he is the chair of the AIAA Materials Technical Committee, and he is bringing new energy into that committee. But also his interests in structural mechanics and micromechanics kind of feed into the way he is bringing that new direction into the AIAA Materials Technical Committee. So I invite people to pay attention to what is happening in that area. So with that, I'd like to welcome Wenbin to start this seminar. And if you have questions during the seminar, feel free to add questions to the Q&A or the chat box. They may get answered as the seminar goes, but at the end, we will, of course, have a discussion, and you will get every opportunity to ask additional questions. So with that, Wenbin, please start your lecture.
Thank you, Sergio, for this nice introduction. I'm honored to have this opportunity to share my research with Caltech faculty and students. I certainly hope that it was a physical visit so that I can get more interaction with you and also appreciate the entire campus. But the virtual is still pretty good. What I'm going to share is what I've been doing in recent years. I've been working on the concept of structured genome, which has the potential to provide a unified multi-scale approach to bridging materials, genome, and structure analysis. Some of you may have heard about the Materials Genome Initiative. The objective of that initiative is try to use computational tools, experimental tools, and along with digital data to develop to use it in an integrated fashion to develop materials faster and cheaper. But if you find out, it mainly focuses on the material modeling at the length scale, smaller than micron in the nano or smaller scales, or hundreds of nanometers. Majority of these are done at the molecular level, and it's not practical for, my background is structure mechanics. So it's not practical to design composite structures at that level. Instead, we will expect the Materials Genome Initiative to deliver us the constituent models and properties and interface properties for the constituents like fiber and matrix and the interface between them. And these properties predicted at this level usually cannot be directly used as the input in the structure analysis. The reason being that the structures we're talking about is at the meters, like fighter, cars, and airplanes and helicopters, meters or tens of meters. Then the fiber we're talking about is at the microns. It's much smaller than human hair. And let me bring out my pointer. Then, it's impossible to include every details of the fiber explicitly in the structure analysis. The reason being that if you're familiar with finite elements, it's even harder to cross two length scales. For example, for a 1 millimeter material block, if we want to capture fiber details, your element size cannot be more than fiber. Then you're talking about millions of degrees of freedom. But here we need to cross 10 length scales from micron to the meters. And we need to, and we also know that structure behavior directly, affected by how we engineer the fibers. So we need to find an effective way to bridge the gap between the materials genome and also the structure analysis. Let me use an example. Traditionally, for example, fiber reinforced laminate. What we do, and we have so-called bottom-up multiscale modeling. We start from some kind of unicell idealized representation of the material mixture, then use certain micromechanics calculation, could be analytical, could be semi-analytical, or could be numerical, and to get so-called nominal constants. Then use some structure series. The most popular one is the classical lamination theory to construct the structure series, then do the structure design analysis. Both micromechanics and structure mechanics, they are two separate subjects. And we have all kinds of models there, and also various assumptions involved. And the more fundamental assumption is what I call here scale separation assumption when you do this two-step micromechanics and structure mechanics. For example, you have a unidirectional fiber reinforced composite and perfect bonding. If you do this way, basically you effectively replace the original structure with this structure made of 3 homogeneous layers. Then you shift the interface, discontinuity interface. Originally the fiber and matrix interface now become layer and layer interface. We create so-called artificial discontinuity. It would be okay if the fibers are much smaller than each layer thickness, which is true for traditional pre-pregs. We have about 20 fibers with the layer thickness. Then for the global behavior, stiffness and vibration modes and buckling, that would be okay. But it would not be okay to get the stress concentration because even the material discontinuity is different. And that's why that for structure behavior, for stiffness consideration, the classical lamination theory do a good job there. But when you go to damage and failure, because damage failure is a local phenomenon, then we have difficulty to have a good prediction. And also for some situations that even the global behavior will be wrong. For example, we have a honeycomb in the middle, a sandwich structure with face sheet in terms of laminate. Then the traditional way, what we do is that if we use the bottom-up multiscale modeling, we take a unicell, do a micromechanics calculation to get the material properties for that honeycomb. Then we treat it as a homogeneous layer to do a sandwich structure analysis. And it will have some issues even for the global behavior. The reason being that the size of the honeycomb is similar as the thickness of the panel. So when the scale separation is not clear, it's not at that 3-dimensional material level, but at the panel level, which means the thickness and the size of the microstructure should be considered together to do the homogenization. And this also could, this kind of bottom-up thinking sometimes also confuse structure behavior and material behavior. Excuse me. I don't know whether you see this paper before. It's published on Science 2017. And what this paper does, they produce a new metamaterial, and they have a weird, strange behavior. Basically, when you apply a tensile force, it will twist. So that's what title means, that the 3-dimensional mechanical metamaterials with a twist. But the twist behavior only exists when when you have finite only a few unit cells along certain direction, for example, you stack them together along one direction, it's kind of like a beam, a metamaterial beam, or stack them together along 2 dimensions is a panel, then you have the extension twist coupling behavior. But if we stack them all 3 dimensions, repeat many times, then the twist behavior will disappear. So it's really not a 3-dimensional material property. What I will call it is a structure behavior. To generate the extension twist coupling at the structure level is pretty easy. And we do that, we can use regular laminates to generate that kind of behavior. So to avoid the issues associated with bottom-up multiscale modeling, I have been searching for a top-down modeling approach from the system perspective. Fundamentally speaking, for a structure, no matter how complicated they are, they can be basically come to the structure analysis. It's a combination of 3D solids, and if all the 3 dimensions of that component are similar size, or plates and shells, if we know some components has 1 dimension much smaller than 2 other dimensions, and also beams, if we know that we have 1 dimension much larger than 2 other dimensions, or thin-walled beams, if we have all 3 dimensions, they are of different orders of magnitude. And this is basically our mathematical idealization. And when we do the analysis and design, we digitalize them as a combination of solid elements, plate and shell elements, and beam elements. And what we have to realize is that this single segment line element could represent a box beam with each wall made of, say, 20 layers of woven fabric. And this 2-dimensional plate surface element here could be a stiffened panel with skins and stiffeners made of composites. And what we need to find out is that the whole, how we can capture the behavior, use this much simplified mathematical representation. And that is what we call the models. Behind each element, there is a corresponding model. And if you're familiar with continuum mechanics, for each structure model, we have 3 parts of equations: kinematics, kinetics, and energetics. Energetics also called constitutive relations. And the kinematics and kinetics will remain the same, no matter if it's made of composites or not composites. What will be different is the constitutive relations. And here I only use linear elastic behavior to do the illustration, and it can go to nonlinear. And what I have to point out is that for composites, particularly anisotropic heterogeneous materials, the stiffness matrix could be fully populated. For example, for the beam theory, we all know the EI, GJ, EA, this kind of beam constants. But for a composite beam, we could have a fully populated stiffness matrix. All the deformation modes could be coupled. So the focus of composite modeling should be focused on the constitutive relations. And the way to find the constitutive relations is what I call the constitutive modeling, because kinematics, kinetics has already been implemented many times in the commercial finite element codes. So the mechanics of structured genome is what I proposed as an alternative to the traditional multiscale modeling. What we do is first we decide what kind of model I want to use to describe my relevant structure behavior I want to capture. Then I decide at which level I characterize my material. Then we need to come up with some method, what is called here mechanics of structured genome, to minimize the information loss between these 2 representations. And some of the theories we developed, they implemented in the code called SwiftCom. It is a formal framework that does not exclusively rely on just direct information passing across scales, but rather operates from the homogeneous behavior, capture details as scales relevant to the particular design needs. This flowchart shows the MSG-based multiscale modeling. We start from the 3D continuum mechanics model. First, we identify the structure gene. Then we use the principle of minimal information loss to mathematically decouple the original problem to a constitutive modeling over the SG. Then also a structure analysis. And the constitutive modeling over SG produced the constitutive models for the structure analysis. The structure analysis usually has been done by the standard finite element codes like Abacus, Nastran, and ANSYS. Then structure analysis will do the analysis, get the global behavior, vibration, buckling, deflection, all that. And but what we want to find is how the material feels. Then we need to go back. There is a so-called dehomogenization procedure. Still get the relationship from the constitutive modeling. Do a dehomogenization, we will find out what happens within the material, within the microstructure. Then you'll find out that to use this method, there's 3 questions we need to ask and answer. First, what would be the microscopic model? So that depends on design need and how the structure looks like. For example, for a helicopter rotor blade, you want to use the beam elements to represent the composite rotor blade when you do a dynamic simulation. And what is the original model? That depends on what physics you want to capture. If you're only interested in the linear behavior, then 3D elasticity model will be sufficient. If you're also interested in say, nonlinear behavior, hyperelastic or viscous elastic, then your original model will be changed. The third question is what is the structure gene? You need to identify the structure gene. Structure gene is the smallest mathematical building block of the structure. And I will explain more because all the others are pretty straightforward, simple, but structure gene has a new concept. That is what I need to illustrate by more details. But before I doing that, I want to use the subject everybody familiar with, any engineering students know is the beam theory, okay? And how we deal with the beam theory, we know all the structures in our 3-dimensional space, they are 3D solids. And we start from the 3D structure, but we know pretty long what we do. We basically look at the cross-section, usually traditional ways to make some assumptions, then do some cross-sectional calculation to get the constants, the beam constants. Then we reduce the original problem to a set of ODEs to do the analysis. For example, this is the deflection, the bending analysis. For the global beam analysis. After we've done that, but we don't stop here. We do this analysis, we get displacement, rotations, and the force and moments, bending moment diagram, something like that, shear force diagram. And but we don't stop there. If we want the failure, we want to say whether the material is strong enough or not. We use a formula like this. Everybody knows this formula to get the stress, to check the maximum stress against the design allowables. So that's that procedure we all know. And if we talk in terms of the language of MSG, then basically the way we calculate the beam constants, E, I, G, J, that's a homogenization procedure. And we have the original model is 3-dimensional model, and we have a microscopic model is 1-dimensional model. We want the effective properties, that's homogenization, and we get the global analysis here. And then the way to get the sigma, the stresses, is a dehomogenization procedure. We go back to the SG, or you can call it the microstructure, to get the local fields or distribution over the cross-section. And this shaded area is what I call the constitutive modeling. So next, let me show this basic steps of MSG to construct a theory. It's very, very simple. We only need to follow 3 very basic steps. Because they're thinking about in terms of 2 models. We have our original model that's starting, but that's too complex and too expensive to work with. We want the simpler models. That's basically multiscale modeling is about. First step is to express the kinematics of the original model in terms of that of the microscopic model. So in terms of displacement, they can be expressed in terms of, say, displacement, rotation of the beam models, right? And then you can get the kinematics. The strains of original model can be in terms of the beam strains and curvatures, and also some unknown function. And usually in micromechanics, we call it fluctuating function. Then we express the information of the original model. If we're dealing with linear elastic behavior, we're talking about total potential energy. So we express the total potential energy of the original model in terms of the kinematic variables of the model I want. You still have the unknowns. How do we find that unknown? To minimize the loss of information. This information of the original model and the information of the model I want. Then you minimize it, then you will find out the unknowns. Then you solve the problem. You have exactly relationship between these two models. And without really a lot of ad hoc assumptions we have involved in structural mechanics and micromechanics. So now let me illustrate more about the structure gene concept. For example, for 3D analysis, and it depends on your material makeup. Could be basically binary composite made of layers, but it's a 3D solid. You want to do a 3D analysis. Then your structure gene will be just a normal line with the segments indicate how many phases you have through thickness. If you only have this binary composite made of 2 layers but repeating, then you only have 2 segments there. If you have unidirectional fiber reinforced composites, you're dealing with a 2-dimensional domain. Remember, it's the smallest mathematical building block because I can take this 2-dimensional domain, extrude along the fiber direction to build that slice, then sweep along the layer direction to build the entire layer, then build through the thickness. So that is the mathematical, smallest mathematical building block. If you indeed have the 3-dimensional heterogeneity, then you have to deal with a 3-dimensional domain. And that's a similar concept like as RVE, but I will tell the difference between this and RVE. And we carry out this 1-dimensional, 2-dimensional, 3-dimensional analysis. We will get the constituent models. For example, if linear elastic, we'll get 6x6 difference matrix for the structure analysis. After you've done structure analysis, we can carry out the dehomogenization to get the detailed stress distribution within the original material. So this is kind of like a generalized computational homogenization method, but much more powerful than the RVE analysis, particularly for some of you, if you're familiar with RVE analysis. I did a comparison. First, that the users don't have to apply the boundary conditions. When you do RVE analysis, that the most challenging part is to apply the correct boundary conditions. And also, our theory automatically satisfies the Mando condition, and we can prove that. And also, there is no pre and post process needed. For RVE analysis, what we do is that we take a block of material, apply the right boundary conditions in terms of tractions and displacements, then we do a stress analysis, right? Then we average the stress, average the strain, we will calculate the material properties. That's what I call the pre and post processing. And it will be faster because semi-analytical, we had many examples show that this method converges faster than the RVE analysis. And also we have the capability to compute 3D properties and 3D stress and strain fields out of 1-dimensional or 2-dimensional, 3-dimensional ST. For example, people also take a 2-dimensional domain to do RVE analysis, but they can only get the in-plane properties. And also they can only get the 3 stress components. And this method can compute the complete set of 3D properties using one analysis. We directly compute the stiffness matrix or tangent stiffness matrix for nonlinear analysis. And not like RVE analysis, apply a certain set of boundary conditions, do a calculation, get the material properties in that direction, that column, then do another analysis, get it in another direction. We only do one analysis. For example, for the fiber reinforced composite, if you look at a lot of other Multiscale code, they will have this picture showing how they do their RVE analysis. But if you use MSG, this 2-dimensional domain will be sufficient, and we will generate the same result. And it's also more versatile, and it's a single theory, but for all heterogeneous materials. periodic, partially periodic, or aperiodic. And also, it does not have to be a rectangular shape. It can be arbitrary shape, and depends on your material. You may have this kind of microstructures. And we find out that for 3D periodic materials, it will achieve the same accuracy as RVE analysis and asymptotic homogenization, if you heard about it. But for partially periodic or periodic materials, it will always achieve the best accuracy. Because we use the principle of minimal information loss, we make sure that the homogenized model and the original model, they have the minimal information loss. And I have a simple illustration here. Usually this is not done by traditional micromechanics lens, but if you view this problem using MSG, actually that's a micromechanics problem, the black aluminum approach. We treat a stack of laminates as a homogeneous material, okay, kind of like a black aluminum. Then the conventional approach, how they do it, they basically, use the classical lamination theory to get the A matrix, then get your in-plane properties. Then the out of plane properties, what they do, they do various assumptions through the thickness, then calculate the, transverse Young's modulus, Poisson's ratio, CTEs. And if we use MSD, we need to answer the question, what would be the original model? Our original model would be 3D continuum mechanics with layer-wise heterogeneity. And the model I want is a 3D continuum mechanics model with homogeneity. And the structure gene I have is the transverse normal line. That's basically what I have, because I can use this to build the entire structure. Then we minimize the energy loss. We can get the full set of the 3D property for this homogeneous material without make various assumptions. Okay, how about when we have a structure like a panel and also have a lot of heterogeneous details, and we want to analyze use plate and shear element, say for example bending problem and buckling problem, then it depends on how this structure is made of. If it's made of homogeneous layers, then the SG will be the transverse normal line, because that is my smallest mathematical building block. I can use this line, sweeping in plane, I can build that three-dimensional structure. If we have heterogeneity along one of the in-plane direction, I'm dealing with a two-dimensional domain. If I have heterogeneity along both in-plane directions, I deal with a three-dimensional domain. What I want is the plate models for the plate analysis. If you're talking about the simple plate element, you're talking about ABD matrix to input to do your structure analysis. So out of this one-dimensional calculation, two-dimensional, three-dimensional calculation, we will get the ABD matrix. Then you do your plate analysis, then you will go back get all the stress components you need within the original structure. And there are a few things I want to point out. That first, that this method provides a uniform theory for all panels. Here I only use plates, but the shells also can be done in a similar way. No matter whether it's sandwich or laminates or kind of corrugated structures or stiffened panels. And in the literature, people have different theories, but here it's just it's treated uniformly. Second is that if you view this problem in a different perspective, if I view this two-dimensional plate and shell surface as a two-dimensional continuum, then every material point will have a corresponding microstructure for us to compute the effective structure properties. Here is effective plate properties. Then this would be my global analysis, microscopic analysis. Then after I've done this, I will do dehomogenization to get the local stress. What does it mean? Is that the structure mechanics for plate and shell series become a spatial application of micromechanics. If you view this as a two-dimensional continuum and view this as a microstructure. So in that sense, we unify structure mechanics and micromechanics. And for example, I still use the same problem, a stack of laminate. Now I know that if I treat it as black aluminum, I cannot take care of the flexure property that well, the bending. So what I do, I want a plate model, okay? So your starting model is the 3D elasticity model with layer-wise heterogeneity. Your end model is a two-dimensional classical plate model. And your structure gene is still transverse normal. And you can minimize the information loss. At the end of the day, you will derive this model with the plate stiffness. And traditionally, what we do, we take the Kirchhoff assumption for kinematics, basically generate a plane strain situation. Then we do a plane stress assumption. Instead of use C, we use Q, right? Sigma ij equal to Q ij KL, epsilon KL. And, but we do know that plane stress and plane strain cannot exist at the same time. And that's contradiction to each other. For this method, we don't have to make that assumption. We just need to minimize the loss of energy between these two models. How about if we have a structure very long? For example, a helicopter rotor blades. If we have a uniform cross-section, or that the blade can be considered as formed by piecewise uniform cross-section, then the structure gene will be the cross-section. And if we also have heterogeneity along the spanwise direction, we're dealing with a three-dimensional block. And what we want is torsional stiffness, bending stiffness for my beam models. So that will be done at the one-dimensional level. And after we've done the beam analysis, we can do dehomogenization to get the stress distribution over the cross-section over this three-dimensional SG. And again, that if you have a structure, as long as it's very long, you want to use a model as a beam using beam element, then this method will help us to produce the right beam constants for you to use, and also to correct the local fields to generate the three-dimensional stress. And as I said, for the plate and shell theory, and also beam theory, is a very traditional structural mechanics theory. But if we view this line as a one-dimensional continuum, then every material point on this line, you have a corresponding microstructure to generate the effective properties. They are effective beam properties, and also help us to generate the local fields. So the beam theory also become a spatial application of the micromechanics in that sense. And some of you, if you have been following my work, I actually started with the beam theory when I was a PhD student at Georgia Tech with Stuart Hodges, solved the helicopter rotor blade problem. So the beam theory, basically, we worked a lot. We almost we completely solved the problem, actually, because it has been funded by U.S. Army since 1988. We still are funded by them to basically make it into their framework. Later, I will mention about it, into their framework to do the design. And it now becomes tools of choice for the helicopter industry and the wind turbine industry. It also provides a very efficient and high fidelity solution for very long paths, cylinder paths, as long as we know one dimension much larger than two other dimensions. This is a very recent article. They used our tool to design a blade for NASA. That's about the theory. Now let me show a little bit of applications. Current active projects apply this method to various type of structures. So the first one is the NASA game-changing development, that is a deployable composite booms. And you can see that it's a very long structure, and when it's deployed, basically it's kind of like behave like a beam. But when it's stored, they are basically placed and shells contact each other. So from the structure perspective. But if you look at the details, it's made of composites, woven composites, simple composites, and viscous behavior is important, and damage and loss of energy is important, and also distortion is important. Supposedly after you deploy it, that it must be straight, but it's not straight, then the effectiveness of your space structure will be affected. And we come up with a multiscale approach to tackle this problem. We can start from the fiber and matrix. The viscous effects really come from the matrix, and go step by step there. And at the end of the day, because the structure is so thin, particularly, when you do your characterization, they use the column bending test to test the bending and the curvature behavior And what we want to compute is this bending behavior in terms of fiber and matrix. And that's a simulation we did for their CPT, kind of like a virtual twin of that test, the virtual testing for that perspective. We also did a simulation of the entire process in terms of the running, storage, and also deployment. This is deployment is a little bit slow here, and we will wait for a minute. So what we did is that in terms of the fiber matrix properties, we can compute the nonlinear plate and shell stiffness, then treat it as UMAT, then put it into Abacus to do the simulation. The elements, we still use Abacus shell elements. And this is deployment. And I think this kind of digital model corresponding to the real test or the real structure can be very valuable to use to explain things and also to reduce the number of experiments we needed. And there's another one. This is very new. And if you look at the Multiscale, there is inherent problem. Basically, at this global level, the material is treated as a point. But we know that the RVE or SG is not a point. We have a finite size. So sometimes because of that reduction, then we always need to implicitly assume the so-called local periodicity. At one point, you should have, in the neighborhood, should have similar RVE repeating. Otherwise, it's not a material. You cannot use RVE analysis. But we do have this kind of situation exist. We don't have this, nicely arranged RVE repeating everywhere. And a lot of time, basically, the heterogeneity is everywhere, and they are different. For example, the composite flex beam, they have a lot of tight drops, and we need to get a detailed stress. And if we do a detailed FEA analysis, it's impossible. Flex beam is pretty thick. You have hundreds of layers. If you want to get accurate stress, you need quite a few layers quite a few solid elements per layer to do the analysis. And certain type of Multiscale must be needed, but the RVE does not exist, or SG doesn't exist. We don't have so-called smallest mathematical building block. So we come up with the idea, say, how about that homogenize that block of heterogeneous material into a homogeneous solid element. This element is a global element I used in the global analysis, but it contains all the heterogeneity. So basically, this is my original model. We still can reason using MST. This is my original model. Okay, the heterogeneous system discretized with elements, many elements. And this is my microscopic model. It's a single homogeneous element. Here it's 20 node solid element. I want the effective stiffness matrix so that I can do the simulation to do the global analysis. But this will help us to get local stress and strains. Then I can do homogenization to get the effective properties. For this purpose, is the effective element stiffness matrix. It's not a material stiffness matrix anymore. For example, 20 node element, you're talking about 60 by 60 stiffness matrix. And after you've done the global analysis, you do a dehomogenization and get all the local stress within the original material. You apply your failure, whatever local buckling criterion at that level. So what we need to do is minimize loss of energy between these two systems. So I had a few equations, but I will take through, not boring you with this. Basically, still the same idea, express displacements in terms of the displacement of the microscopic model. For this purpose, now it's the microscopic nodal values. And I have some unknowns, then I can get the strains, and then I can write out the strain energy of the original heterogeneous system and express in terms of the nodal values of the homogeneous system. And I can minimize the energy loss, then solve for the unknowns. And here, of course, we need to apply some constraints. Constraints first for the microscopic nodes, these nodes here, because that's the global element. And the real displacement should be the same as what we calculated in the global structure. And then how the surface element, how these nodes are not captured in the global analysis, then there are several ways to apply. It depends on your situation. If it's a stress-free, then we should let it free if it's a free surface. If it's connected with other surface, we need to use so-called periodic boundary condition. In such a way, we allow it to vary in certain fashion. And in terms of the nodal global nodes and also shape functions, then you have another additional flexibility there. After we do the minimization, we will come up with solve a linear system. Then plugging it back to the energy, we'll find out this energy of the heterogeneous system expressed in terms of the global nodes. And that is the 60 by 60 stiffness matrix I'm talking about. And after you have the effective stiffness matrix, element stiffness matrix, you can use the user element in Abacus, put that stiffness matrix into that user element, then you can carry out your analysis. After you've done your analysis, you will get the global nodal values. You can go back to do the dehomogenization, get the local stress and strains. And we did a very simple example, three-layer composite cantilever beam. And we have a complex loading at this end and cantilever here. And it's made of composite resin and some isotropic material. And of course, this is simple enough. We can use hundreds of thousands of elements to do the three-dimensional analysis. We can also simplify in such a way, use 40 MSG-based UEL only. So I will take a chunk of material here to compute the effective stiffness matrix for each of these because they are the same makeup of the material. I only need to do once. The homogenization need to do once. And then do the global analysis, then do the dehomogenization to get the stress. And we know that when we do this homogenization, usually we cannot handle the boundary very well. What we can do is that we can keep the boundary still using the original discretization. And only the middle part I will replace with this new user element. And now I have 32 MSD-based user element and also have this regular solid elements. And if you look at the results for this problem, we did a DNase, which is mesh everything with very fine mesh. And also pure UEL means 40 UEL elements. Partial UEL means at the two ends. And you have the DNase part and in the middle, this is partial UEL. And the results I take is here, very close to the boundary. Actually, if I take it close to the boundary, then they are the same. But this pure UEL, they will be very different. But I take this second here is close to the boundary, but it's already homogenized. We find out that pure UEL do a good job, not for very small stiffnesses. This transverse stiffness stresses. For the implant stresses, to both approach works okay. But for the transverse stresses, although they're small, could be very important. For example, delamination, right? And when we use the partial UEL, it's significantly improved. It's very close to the UEL, but the pure UEL has pretty significant difference. So this method really works pretty well, and we are happy about that. And also another issue about multiscale modeling is, when you look at that for, we can link from fiber to the structure behavior. That's good and cool. But if you look at our inputs, we need in terms of, fiber matrix properties and the failure criterions and also the microstructure. Those are the assumptions. And usually it's very difficult to measure the full set of fiber properties, right? And also when we do that link, although the structure analysis is pretty efficient, but the multi-scale analysis is still pretty expensive, although our theory basically come up with most efficient approach, but still time consuming. So there are a few limitations, computing time and the unknowns of the constituent models and properties for the constituents and interfaces and the geometry and topology of the microstructure. That's where machine learning can help us. And that's, it will help us reduce the time by we do, scientifically guided physics-based multiscale modeling, then construct the surrogate models trained by machine learning. That's most of machine learning work others have been doing, basically come up with a better surrogate based on data. Data could be high fidelity physics-based simulations. Secondly, that to learn this microscale models and properties using major data, but major data is not at that scale, but at the structure scale. And we can use physics informed or physics constrained or physics guided machine learning. Also, we can construct the digital microstructure out of the major data using machine learning. So we have been focusing on to understand the unknown, particularly the failure criteria. We have Haixin, Sai-Wu, but they are all assumed. They may feed a bunch of data, okay, but their predictive capability is very limited. So what we do is that based on the experimental data, we try to link the system from the experimental data. And we link in such a way that if we know that they have existing physics, I will use physics model to link. If they don't, then I will use ANN artificial neural network to link it. We could have multiple ANNs and also multiple physics models. Let me use a very simple system to illustrate. For example, that I did an experiment at my laminate level. Okay, I want to figure out the failure criteria at the laminar level. And what I do is that usually I can have some kind of UMAT that plug into Abacus if I know my failure criteria. It doesn't implement it in Abacus yet. Then I will implement as UMAT. Then I can do the simulation and match the experimental data. So use this. What we are doing here is that I try to replace that UMAT with the ANN, with the neural network to be trained by the data measured at the global level. So that is the case because we don't know the UMAT. I don't know the failure criteria. So it's a black box of the ANN. In certain fashion, basically what we did is that we take this machine learning tensor flow, this kind of package apart, and use what they needed. Okay, so we express the constituent relations, use neural network. We don't know, it's a black box, it's a free form assumption, if you want to call it. There are ways and bias. That's what we need to determine by system level measurements. So system level measurements is passed through Abacus there, and there are sensitivities with basically Abacus and the ANN should be constantly communicate with each other so that we can train the model. We had an example, and basically this is our true model. It's a built-in damage model in Abacus. We did a laminate and a simple loading system. We will say, can I learn this damage model? Use this system. I don't, because this is something, it's ad hoc anyway, but I treat it as a true model. I want to learn that model. So use whatever I do a test at this level and observe force and displacement at certain points, connect that the data to train my ANN. I replace this as AN, so I don't know this, okay? So that is the result. We found out this is the comparison between the trained data and predicted data. We also have some other data which is not used for training. It's just used for validation. We also found out that we have pretty good agreement, particularly for the axial behavior. It's a nonlinear behavior. At a certain stage, it becomes damaged. But for the axial force and lateral displacement is linear. If you look at the model, you will find out that the flexibility matrix, this term actually is not damaged at all. So that's why that is happening. We not only can, this system not only predict the nonlinear stress force and displacement behavior, we can also generate the stress and strain curve, nonlinear stress strain curve. Although we don't have a mathematical formula to describe it, but this becomes a trained model, and that trained model can be used as a UMAT for engineers to do the design, which is particularly for their material. And since we are basically focused on method development and tool development, then we also take technology transfer very serious. And if you're interested, and if you know CDM Hub, we made our code available on CDM Hub. You can just log in, and then on any computer, you should be able to carry out those analysis I just mentioned pretty easily. You even can do it on your smartphone if you want to do it. We have one code called GMesh for FC. We integrate our code with GMesh. It's for general microstructure. You can do honeycomb and sandwich structure and all that. And we also integrate our code with TextGen. We can deal with textile composites and call SwiftCon to do the homogenization, dehomogenization. We also create apps for students, for people who might be interested. It's in terms of iOS and Android, and we have the capabilities. You have the interface on your phone, but actually the back-end calculation will be connected back to our server at Purdue. And I mentioned about this, what we are doing with Army right now, they call the Galaxy rotor design system. And I think this is our part. And what they try to do is a digital engineering system they have right now. They want to have all the components for the helicopter design linked together. And this is one of the work. And also we integrated with CATIA. When you do the aircraft design, you have a wing and you want to get the elastic axis and torsional stiffness of that section. You can cut a cross section, then you can invoke our code to get the sectional properties. We also integrated with HyperMesh and OptiStruct. That's available now through Altair Partner Alliance APA. OptiStruct is our optimization code, if you are not familiar. It's a pretty good one. And we also integrated with Abacus. We have this capability enabled for Abacus so that you still take advantage of the traditional finite element analysis capability of Abacus, but with the Multiscale constituent modeling capability provided by MHD and SwiftCon. We also integrated with ANSYS. If you are ANSYS user, you have this capability through classical ANSYS or Workbench. And we also integrated through with Nastran. You could have all these material systems and still use traditional Nastran elements. So as conclusion, the mechanics of structured genome bridges the gap between materials and structures to harvest the full benefits of materials genome initiative. It provides unified modeling for structures and materials featuring anisotropy and heterogeneity. It can eliminate invalid scale assumption, scale separation assumption, and also assumptions within scales. And we can achieve the DNS accuracy and the efficiency of simple engineering structure models. And it enables us to model composites and in general heterogeneous and anisotropic materials as simple as metals, capturing details as needed and affordable. You as an engineer, you do need to decide where you start, where you end. And it can power conventional structure tools with accurate constituent modeling for anisotropic heterogeneous materials and structures. And last but not least, and this method unifies micromechanics and structural mechanics for multi-scale constituent modeling. in this book, The Creative Aspects of Science by Jacob Bronowski. They mentioned that the progress of science is the discovery at each step a new order, which gives unity to what had long seemed unlike. Faraday did this when he closed the link between electricity and magnesium. And Maxwell did it when he linked both with light. Einstein linked time with space, mass, and energy. So science is nothing else than search to discover unity in the wild variety of nature. And for us, this MSG actually provides a new order or new way of tackle all kinds of structures in a unified way. And I'm pretty satisfied with this academic value of this methodology. This is the last chart as kind of like a summary that this is all the SGs we tried before. We have tried many others. You can see that the SGs can be arbitrary shape and can be 3D woven, can be metamaterials, can be short pipe systems, and it can be curved. And it will provide, it can be used for virtual testing of materials. We did, we showed the CPT test, right? It can be get the mechanical properties or multifunctional properties, and also can use that as component for the multi-scale modeling of structures. And as we mentioned, we deal with all types of structures, regular composites, different structures, built-up structures, and sandwich structures. So that's all I have. I will stop here and to see whether you have any questions.
Thank you, Wenbin. Since I'm chairing the session, I will ask the first question. And